Okay, so yesterday we established that rate of changes are just the slope of a line, and we have the suspicious procedure I called taking the derivative, where we did some funny exponent subtraction. Usually that only happens when you like divide by 1 power of the number, right? Then you subtract 1 from the exponent. We magically did that without any division, it seemed. And then we also multiplied by some number, by the old exponent. Okay, and so we had the derivative and we did the antiderivative where we just reversed the procedure, but be really careful because it's new versus old exponents or coefficients. And so when you go backwards, that the order is changed. So the derivative is the, I want to say, instantaneous rate of change. We did talk instantaneous in honors physics. But then we didn't do much of it, right? Like if I wanted the rate of change or the value at some instance, well, either you could solve it for time, you plug in the time that I told you that's that instant. You okay, Alan? Okay. Or I would want the slope of a graph for instantaneous rate of change right at that point, and it was kind of obvious, like the whole graph would have that slope, because we didn't have many changing slopes in honors. Well, oh no. Okay, so your calculus students now, you can deal with, okay, I have a function of time on my y-axis, and I have time itself on the x-axis, and we'll just do some weird curvy function in green. Could be any polynomial. Okay, once its rate of change at this point, well, I can actually take a ruler and kind of draw it, or even without a ruler. It's the slope of the line at that point. Okay? But if I've got some weird function, how am I going to mathematically solve that? Okay? Well, remember, your rate of change on an xy graph, the good old slope is just delta y over delta x. So let's call this point t that I'm interested in. I'm going to make another point, and that's going to be time point t plus, we'll call it s for something small. Some small amount of time. Do you don't like? Do you object to that because it's the same symbol for seconds? There's other fancier calculus symbols for that, but we could make it a sigma or a capital S. I'm going to write down that it's something small. We're going to increase t a small amount of time beyond the point we're interested in. Oh, so I would have a different slope like that. But then I'm going to actually take this something small and I'm going to have it approach 0. And that, can you see that? That shrinks those points closer and closer together. If I make S, and you literally, so when I was a student at Purdue, we wrote computer programs where we input some function or we approximated whatever, the temperature, the weather, whatever we were interested in modeling. And then you just cut it down to like, okay, now it's a tenth of a second and a hundredth. Now it's a millisecond. Now it's a microsecond. You just jump the time interval down and down and down, and the computer can calculate it until it's so small it's like small enough. But it's not 0. Okay, so you can substitute in, and now they use supercomputers for this to do massive models. You're just substituting in smaller and smaller numbers and see how it looks. Right? The smaller the number, the more calculations the computer has to do to graph this whole thing. Right? If every box is, if you do millions, if you do milliseconds, every box is 1,000 points. But if you do microseconds, every box is 1,000,000 points. And 1,000,000 calculations it has to do. Well, so we have, what are they called? Petaflops now? How many calculations in a petaflop? It's a ridiculous number. Okay, but that's why they need so many. They're doing massive models of the whole planet sometimes. Okay. But anyway, for today, I just want the slope. And so, okay, like delta y. Let's. Yeah. We'll zoom out a bit. The idea is simply this. My slope is, we talked about t. I evaluate the function at t plus s, my small little point, minus f of t. And then on the bottom, I'm going to have, it's delta t for the change on the x-axis. It's just t minus t. Oh, no, it's t plus s. Excuse me. It's Friday. Let's do that. It's t plus s, parentheses for my own sanity, minus t. Oh, so I'm going to actually divide by s. So I'm going to shrink this down and down and down until my divisor is small enough that I can agree that it's exactly the point I want. Okay, and I'm going to take the difference in those functions. Sounds simple enough, right? Any questions? Okay. So I got to hit you with this. I bet you saw this actually starting in pre-calc, because it's actually such a simple idea and operation that they usually explain it to pre-calc students, but the consequences of this are pretty insane. And then I can remember in like 4th year physics at Purdue, we were still learning new consequences of doing this. So we're going to calculate the slope, and we're going to take, it's called the limit. So we say we're going to LIM the slope, LIM of m, as s approaches 0. Okay? Let's put that in brackets. Has anyone never heard of taking the limit before? If you haven't, maybe because you just started Calc AB or something. So you gotta be honest, you're gonna be lost. If you lie and don't tell me when you've not seen this, okay, I believe you. Our math department is pretty awesome. I'm now part-time part of it. Yay. But okay, if I'm way beyond you, okay, you gotta slow me down. My 5-year-old struggles with that. She doesn't want to tell the truth. Yes, I have had an ice cream. Oh, no, I haven't, because then I can get one. Okay. All right. Anybody still need that page? Okay. Because here we go. All right. Let's do an example where we say our function of t is going to be minus 5t squared. Okay? And then here's our problem. Can we do that? Hopefully it likes that. I'm going to take the limit of as little s goes to 0, and here's my function. Okay, I like a big bracket just to kind of organize my thoughts. I have t plus s squared, and then minus negative 5 times t squared. And then on the bottom, I have t plus s minus t. Aren't I about to divide by 0? It looks like I'm going to try to. But we soldier on. Okay. I think I need a whole other line to write out the consequences of this. Alright, so we FOIL that t plus s, because I added some little bit of time. Yes, indeed, I lose everything on the denominator except little s. Awesome. Let's see if I can do 5 in my head. Okay, we have t squared plus 2ts plus s squared, okay, and then plus 5t squared over s. Any complaints about that? And we still, to save space, I didn't write, we're taking the limit. Yes, no? Yep, yep. Don't think I made any mistakes. It's always hilarious when I do. Okay. All right. Oh, well, look. If I distribute the 5, I have minus 5t squared plus 5t. So that one goes away. So I'm taking the limit as s goes to 0 of minus 10 times t times s, and then I have minus 5 s squared all over s. Did I do anything wrong? Minus 5t squared plus 5t. Okay. Write lightly. Okay, so I actually want to evaluate these differently. I don't want to blast out that s. Okay? Because it's a different consequence for everything. Look at this first term. I should have changed colors. You can tell what's going on. Okay. In the first term, minus 10t times s, canceled out the s's. Oh, I don't have to divide by 0. And that other one had s squared. So I cancel one on the bottom, and now I just take that to 0. So I had the limit of my small amount of time going to 0 of this strange slope function equals just minus 10t plus 0. Cool. I didn't have to divide by 0. Any questions? Do you see the connection? Oh, some people kind of do. It's Friday, and you just explained how you don't sleep. Let's write it a little more clearly then. Okay, I'm taking the limit of the slope. My small amount of time becomes 0. Oh no, I want my actual function in here. Sorry. Being ridiculous. Okay. We'll say, oh, what do I want? No, I need, okay. Oh, yeah. We'll say delta f over delta t. Okay, and we just wrote that down. Okay. And I said that's the derivative. So that's the d dt acting on the function of t. Okay. And we could have called that from yesterday f prime of t. So I'm trying to say, take the derivative, and it's really this limit procedure of minus 5t squared, and you get negative 10t. Do I need to prove it in the general case, where I do a times n to the integer power? Maybe I'll do that as a separate video for fun. But look, I took one away from the exponent, minus 1, and I multiplied times the old exponent over there. That's just what ends up happening. Okay. Do you remember a physics formula where, like, what kind of physics quantity might be minus 5t squared? Sure, Kevin. Exactly. That is the vertical displacement of an object dropped from rest near the center of the Earth. And if I have then like delta y over delta t in my crude honors physics, that would be the velocity. Well, welcome to AP Physics, where velocity is just derivative of y with respect to t. Okay? And sure enough, so that's minus 10t. And if I took, on the next one, if I took dv dt, it would be, oh, negative 10. And that's the acceleration. Okay, so I'm going to ditch all these little deltas. You have a more powerful tool now. If you want the displacement, you can just calculate, plug in the times and subtract, okay, to get displacement or change in v or change in t. We now have the power to find the instantaneous velocity, instantaneous acceleration, using this derivative procedure, as long as we have a function. So your homework will feature a lot of functions with powers of time. Okay, all you do is you subtract 1 from the exponent and multiply by the old exponent out front, and you can do it term by term if you have a polynomial, and that's the rate of change. Okay, and that absolutely does. Velocity is now the time derivative, the rate of change in position or displacement, so you're going to have the same rate of change. And acceleration is just the time derivative of velocity. And now, if you have an acceleration function, you can take a derivative of that. You get what's called the jolt. And then there's something else, and you just go and go and go, and you can calculate rate of change and everything. Okay? Any questions? Okay. There should be. And it really... So, this limit procedure, where I added a little s, how can I guarantee that you can just subtract and multiply, subtract an exponent and multiply? Oh yeah. By the way, we have little d dt. That's of course t to the 1 power. That actually signifies that we are only subtracting 1. Right? I could, if I was a crazy mathematician who for some reason majored in math, you can differentiate with respect to t squared. You can differentiate with respect to whole function. This d dt on the bottom is actually telling me only take away 1 exponent. And then you're just supposed to know this procedure, and you multiply by the old exponent. It's your calculus teacher's job to teach you. So this procedure, this is what you will do. You'll take the limit of the change in the function over the change in time, some infinitesimal change that's shrinking away. That's the calc class's job to do sine functions, non-polynomial functions, all kinds of crazy functions. Yes, look at what you've done to your life for the next year. If you're taking calc this year, you're going to just learn to do so many derivatives. You're going to work out that terrible procedure. Actually, this time it wasn't so bad. And you're going to find out how to take derivatives, a bunch of other stuff. The AP equation sheet has the answers to the derivatives that you really need to know. So in case you forget how they come out, then they're right there for you. But you need to remember when to do this and what that means when you do your little ddt, or you can do ddx. Okay? Monomials and polynomials is all we need for 80% of physics. So there you have it. Any questions? Alright, it is Friday, so we're going to stop the first video there, just for fun.